Good morning. Today we'll be talking about step scattering from a step potential. But as always, we'll have a brief discussion of what we did last time. Last time we talked about the finite square well. We patched together the left side, the right side, and the center of the well to get these fairly complicated solutions that we solved graphically. And we used an understanding of, or analysis of, the infinite square well and the simple harmonic oscillator to get the correct answer. Okay, so we have our finite square well here. There's some particle with energy E inside the well. It has potential V naught, bounds minus L over 2 to L over 2. And the solution to the wave function kind of looks like this on the left side and this on the right side, meaning that there has to be decay when the energy is less than V naught. Okay? That is, the wave function has to decay when it is less than V naught, when its energy is less than V naught. Recall that for x greater than L over 2, we have this e minus kappa x solution, where kappa is root 2m v naught minus e over h bar, and x less than minus L over 2 is e to the plus k kappa times x. Okay, these are decaying solutions for the right side and the left side. And essentially we solved it by considering solutions of the form and that is to get the energy values we considered tan of psi and the square root of functions of psi where psi is root 2 me over h bar, and psi naught is L over h bar root mv naught over 2. And our goal here is to solve this expression tan of c is equal to root c naught squared minus c squared over c. Okay, and again we solve this equation graphically. So as function of c, we plot tan and square root function, and this is the tan here. You probably recognize that. This is the square root, function. And so for small C0, you have a curve that looks like this. Just to make it really clear, this curve here is the square root and this curve here, as I said before, is the tangent. Okay. And this particular solution was for even functions. For instance, for n equals 1, the ground state, you have cosine type functions. Okay. In the last class, we also did odd functions, which I won't review again right now. So before we've been talking about pretty much when the energy of the particle is less than V0, but what happens when the energy is greater than V0 and one side is not bound. Okay, so this side goes away and this becomes this step, which is the topic of today's focus. So what happens when E is greater than V0? That is the question. So consider the following. The situation described before. This step potential with particle energy E, potential step V0, and V equals 0 on the left hand side. That's for negative x, and this is the x-axis, just so it's quite clear. Okay. And so how do we tackle this? Well, we write down the time-independent Schrödinger equation, as we've been doing for the past few classes. So let's consider that once more. This is the time-independent Schrödinger equation you've come to know and love. And for this particular case, we can consider the following expression. For constant V, we can label this E minus V0 term K0. In particular case squared, where k naught is root 2m e minus v naught over h bar, and k, as you know, is root 2m e over h bar. So if you notice, this is quite similar to how we started for the finite square well. In some sense, this is just half a finite square well. And what did we do before? Well, we broke up the problem into two pieces. So let's do that now. Okay, so region 1 and region 2. So now let's consider both regions 1 and regions 2, and start with region 1. And that's for x less than 0, e greater than v naught, and v naught in this region is 0, and k will be v0k root 2me over h bar, which we know is greater than 0, and we know we have solutions that look like these exponentials that are oscillating. By oscillating I mean they have these eyes out in front, these imaginary numbers. So they'll form cosines and sines. Okay? Now for region 2, the situation is more interesting. This is the region where the energy is now less than V naught. And we write a K naught that's equal to root 2m e minus v naught over h bar, and we define the square root a little bit differently. You can write this as imaginary number 2m v naught minus e, where v naught minus e is a positive number, all over h bar, and rewrite or define kappa to be this square root term. Okay, by definition. And therefore, the solutions you end up with, c e to the I k naught x plus d e to the minus I k naught x they can be written as c e to the I kappa, sorry, e to the minus kappa x plus d e to the plus kappa x, where we know that we need to have, for x tending towards infinity, we need to have the d term go to 0. So that needs to go away. And we expect a graphical solution that looks a bit like the following. Attempt to draw an oscillating solution for x less than 0. And a decaying solution for x greater than 0. Decaying towards 0 amplitude. But what happens? So far we've talked about E less than V naught. But what happens when the E is greater than V naught everywhere? In that case, it's looking a little bit like this one, except of course that E is greater than V naught everywhere. Okay, so now we have this case. E is greater than V naught everywhere. And let's again label this region 1 and the region 2. And we'll once more solve the Schrodinger equation and attempt to figure out what the solutions look like on the left side and the right side in region 1 and region 2. So let's look at region 1 first. Okay, and this is familiar. It's V naught is 0, and there's some energy. We've done this before, so that should be familiar. But region 2 is a little bit unusual or unfamiliar. So for x greater than 0, E is greater than V naught. We can write down K is root 2m E minus E naught over H bar. Okay, and this K remains a positive in the square root, so it doesn't become something like a kappa as we found before. And the solutions look like, go like C times e to the I k. Let's call them k naught. I should call this k naught. X plus d e to the minus I k naught x. Okay. So what does this look like? Okay, so the traveling waves will essentially be the following. Let's consider an incident wave coming from the left. And so if it's coming from the left, you'll end up with this sort of situation that, let's draw it here. Traveling wave coming from the left, heading to the right, which we will have plus ikx. And traveling wave going from the left to the right, right to the left, going in this direction, that will represent e minus I kx. Notice that the signs are different here depending on the direction. And on this side, region 2, you have a wave going to the right, and a wave going to the left from the right. And that's k naught now this time because the VE minus V term. V is non-zero this side. Okay. And to this makes some things clear. E to the plus I kx represents the flux coming from the left. E minus I kx represents flux fluxed from the potential. Okay. This is really for region 1. Therefore, we can try to write down wave solutions on both sides. For the side of x less than 0 and x greater than 0. For x less than 0, let's say it's a times e to the I kx plus b e minus I kx, where k is, as usual, root 2me over h bar squared. And for x greater than 0, we have c e to the I k naught x plus d e to the minus I k naught x, where k naught is root 2m e minus v naught. And this d must be equal to 0, and that represents no incident wave coming from positive x, positive x equals infinity, x equals positive infinity rather. Okay. And if we were to draw that, draw the solutions that we find, essentially make a diagram similar to this one. But let's make that more concrete. So we go and follow all the steps that we need to follow to make things really clear. Okay. Great. So what we have is this traveling wave to the right, going from the left. It's a e to the I kx. Going to the left from the right is e to the minus I kx. And just emphasize that e is greater than v naught here. Okay. And let's see, let's move this energy this naught bit. And some space. And on this side, you have c e to the I k naught x, and this one has d e to the minus I k naught x. Notice this is coming in from plus infinity, which hopefully makes it clear that it can't exist for this case when the wave comes in from the left here. So we make that a 0 coefficient. Okay. To keep the interpretation, maybe I'll put this in kind of small so it's still clear. Okay. So what's next? So as you should notice here, there is some reflection from a wave coming in from the side, from the left. It gets reflected by this barrier. This is the interpretation of this wave with the B coefficient. And then there's transmission. There is this wave over here with the C coefficient. And then this wave is the wave you basically interpret as the transmitted wave. So incident wave, reflected wave, and transmitted wave. Okay, so there is, let's make a point of emphasizing that. Reflection and transmission. There is reflection and transmission. And what we can do is use the idea of probability current we saw a few weeks ago to try to quantify what fraction of the wave is reflected and what fraction of the wave is transmitted. And let's recall that the probability current looks like the following. H bar over 2 mi brackets phi naught d phi dx minus phi d phi star dx. Okay, and by definition, so. Now with this tool in hand, we can define the reflection coefficient R to be the reflected probability current divided by the incoming probability current, and we can define the transmission coefficient as, you guessed it, the transmission coefficient probability current, or the transmitted probability current I should say, divided by the probability current for the incoming wave. Okay. The picture you could have maybe something like this. Where you have a wave packet going from left to right and then getting reflected at the barrier and going from right to left. And again, this is x equals 0, and this has V naught, barrier V naught, and energy E. Okay, so these are the incident and reflected wave packets. Recall we can get wave packets by taking a sum of eigenfunctions, eigenstates, a superposition of waves, where the coefficients are a of k, and the waves are sums of these e to the I kx minus omega t. Okay. Now let's pivot towards tackling an in-class assignment, or 2 or 3. And let's do in class 1, 2, and 3 next. And when you return, let's consider a different limit, different case for the energy being less than V naught. Okay, so let's draw one more of these step potentials. Energy here is now less than V naught. This is E. This is V naught. Clearly, E is less than V naught. Of course, instead of where it's greater than V equals 0. And remember that the wave is going to be kind of oscillating here and then decaying once it hits the barrier. Okay? Let's recall this solution for this bit. And as always, we try to get the solution by first writing down the Schrodinger equation we know and love. It's minus h bar squared over 2m. The second derivative of phi with respect to x plus v of x, potential phi of x equals E times E of phi of x, and for x less than 0 for this left hand side, we know by now that k is root 2m E all over h bar. For these k's, E is greater than 0. And we can guess solutions. And you should know this by heart right now. Phi is e to the I kx times a plus b e to the kx. I made a mistake here, so I should make this a plus. And now for the x greater than 0 case, what we have is the following: k naught is root 2m E minus V naught over h bar, and that is equal to I root 2m V naught minus E all over h bar. And we write it like this to emphasize that this this term here, where the E is is greater than the V naught is greater than E, basically allows you to pull out an imaginary number and have this argument of the square root as just some positive number. And recall that this object has solutions phi c times e to the I k naught x plus d e to the minus I k naught x. Okay. And because the k naught has an imaginary number in there, I can simplify this a little bit, and we get in the end c to the c times e to the minus kappa x plus d times e plus kappa x, but because d is has to go to 0 because we want to avoid unphysical solutions, this simplifies the expression even further. Okay, so we can ask yourself the question, from all this work we've done, what is the transmission and the reflection probability? Okay, so let's take a moment to do in class 4, and when you come back, we will look at a slightly different case linked to the discussion from the optional in-class assignment from last class. Okay, let's do this on another page. So let's reconsider the case when E is greater than V everywhere for the finite square law. That will change things quite a bit. And let's see, let's draw our finite square law once more. Looks a bit like this. Okay, let's try again. Looks a bit like that, where this is the energy of the particle, E, greater than V naught here, and again we have minus L over 2 here, and plus L over 2, where this is the kinetic energy, and we have again region 1, region 2, and region 3. Okay, this is region 1. And recall that the energy, total energy, is the potential energy plus the I misspoke. Total energy is the kinetic energy plus the potential energy. Alright, so let's do this. What do we do? Of course, we break things up into different regions. Region 1 first, then let's do region 3 next, because it's similar to region 1, and do region 2 last. So in region 1, we have the following. E is h bar squared k naught squared over 2m kinetic energy plus the potential, where k naught is root 2m E minus V naught over h bar. Okay, and note that when k naught is small, that lambda grows large. Okay, for region 2, let's do region 3 first. For region 3, we again have E is h bar squared k naught squared 2m plus v naught. Essentially, it's the same as region 1. And region 2 is a little bit different. Region 2, E is equal to h bar squared k squared over 2m, where k, as you remember, is root 2m e over h bar squared. Okay. And interestingly here, k is going to be large. Certainly larger than the case for region 1 and 3. Therefore, the wavelength will be small. Okay. And the solutions are, can you think of what the solutions are? Yep, you guessed it, e to the plus or minus I kx and e to the plus or minus I k naught x. Maybe you included some coefficients there, and that's also quite fine. Okay, so I want to dwell on this last point a little bit more. The fact that k naught is small and the wavelength is large in these regions, and when the k is large, k is bigger than here because of the term of the square root, then wavelength is going to be small. Okay, so small wavelength here, big wavelength here and here. Large k, small k. Alright, so what will that look like? It turns out that will give us this interesting picture. Let's see if I can draw it properly. Let's draw the well one more time. And let's see, let's draw in the energy here. That's not too bad. That's E, V naught. Choose your well. And the wavelength will be large in this region 1. And then, as we said, it will be small region 2. And again, large in region 3. Okay, something like that. That's not the best drawing, but you get the idea. And clearly the amplitude here is bigger. I'll switch that. The amplitude is smaller here than it is here. Notice I'm drawing this way for a reason. And why is that? So region 2 has a smaller amplitude and therefore smaller probability density, psi squared. Okay, So let's consider the following. Let's call this an aside. It's not something you really need to know, but it's more for fun. Let's consider some wave function that goes like sine k of x. And let's call this equation 1. So let's change this to k naught to keep the conventions the same. And let's, for fun, take a derivative with respect to x, just to see what's going to happen. Let's call this equation 2. From equation 1, which is that, we can square both sides and get this expression. Okay, let's call this equation 3. It's bigger than I wanted it to be. Okay. Now picking back up from here, let's do some algebra. So I'm squaring the function both sides and dividing by k squared. And if I do that, I get the following. Okay. So why are we doing all of this? Well, we want to simplify these expressions. It looks like we have a sine squared over here and a cosine squared over here. And so we can try to relate k to the amplitude by comparing these two terms. So let's try to do that. Let's add equation 1 and equation 4 and get the following. Sine squared plus 1 over k squared d psi dx squared. And that goes like b squared sine squared kx. Well, I think I'm dropping my k naught. I'll go back and I'll fix it. Or let's actually, I don't want to write k naught everywhere, so I'll just take it off from here. And yeah, so this k, I'm redefining it to be like this, which is fine for this example. Alright, sorry about that. So let's go back to here, where we have combining these two terms, equation 1 and equation 4, this is not a 1, it should be a 3. Now, combining this with this one, 3 and 4, you're going to put this, which simplifies to a squared sine squared kx plus cosine squared kx as promised. And what do you do with that? Well, end up with a is sine squared plus 1 over k squared d psi dx squared square root. Kind of a mess, but we don't really need to go further than look at a and k. And when a decreases, k must increase, and that means that the wavelength is also increasing. So that explains the relationship between the amplitude and the wavelength. So that's it for today's lecture. Looking forward to seeing you in the next class. Bye-bye.